Hello. This time we're going to calculate and determine a basis of the null space, the range and the row space of a matrix as the one that I'm indicating here. And we're also going to verify the dimension theorem and describe some of the methods associated with finding such bases. So let's start. So for the first one, let's recall that the null space of A is described as the collection of vectors, in this case in R4, such that the product of the matrix with the vector is equal to 0, the vector. Now, you may rewrite this and expand it in this fashion. You may say, well, this is a collection x1, x2, x3, x4 of vectors in R4 by explicitly describing the components of the vectors times 1, 2, 2, 1, going row by row, 2, 2, 1, 0, 1, 0, negative 1, negative 1, times x1, x2, x3, x4 equal to the vector 0, 0, 0. Of course, this is nothing else but a system of linear equations, a homogeneous one. And from that one, we can extract an associated augmented matrix. The description of this set involves a system of homogeneous linear equations. What would be that system? Well, the one that is associated with this augmented matrix. 1, 2, 2, 1, augmented with 0, followed by 2, 2, 1, 0, augmented with 0, 1, 0, negative 1, augmented with 0. Of course, nothing new under the sun here. Now this time, we're going to apply a row reduction process to obtain an equivalent solution or description of the solution to this system of equations. And for that, I apply the following operations. To row 2, I subtract twice row 1, and to row 3, I subtract row 1. And then I obtain the following matrix: 1, 2, 2, 1, augmented with 0, followed by 0, negative 2, negative 3, negative 2, 0, followed by 0, negative 2, negative 3, negative 2, 0. Of course, from this point, we see that there's an obvious reduction that we should perform, and that would be the following. To row 3, we subtract row 2, thus obtaining the following matrix: 1, 2, 2, 1, 0, 0, negative 2, negative 3, negative 2, 0, 0, 0, 0, 0, 0. Then from here, I multiply the second row by negative 1/2 to obtain a pivot. So I have 1, 2, 2, 1, 0, 0, 1, 3/2, 1, 0, 0, 0, 0, 0, 0. So I'm showing the whole process. And finally, I'll take an additional row operation, which would be to row 1, I subtract twice row 2 to obtain the following matrix: 1, 0, negative 1, negative 1, 0, 0, 1, 3/2, 1, 0, 0, 0, 0, 0, 0. Okay, now, what is that we read from this system? Well, recall that this is nothing else but an equivalent description of the definition associated with the null space of A. So here I'm indicating x1, x2, x3, and x4. So what I'm going to say is the following. Then a vector x1, x2, x3, x4 is, this is the symbol for set membership, in the null space of A, if and only if, well, the components of the vector satisfy the following system of equations. x1 minus x3 minus x4 is equal to 0. x2 plus 3/2 of x3 plus x4 is equal to 0. If and only if, by performing a manipulation here, that x1 is equal to x3 plus x4, and that x2 is equal to negative 3/2 of x3 minus x4. This allows us to make a rewriting of the vector itself. So the vector should have the following format. It should be x1, x2, x3, x4. I can express both x1 and x2 in terms of only x3 and x4. So I'll incorporate that information here. x3 plus x4 for the first entry, then negative 3/2 of x3 minus x4 for the second, then x3 and x4. And this is something that you have seen in terms of algebraic specifications. So now I'm going to decompose this vector into two terms. The first one, x3 times 1 negative 3/2, 1, 0, then followed by x4 with 1, negative 1, 0, 1. So what is it we're saying here? What we're saying here is that every single vector in the null space of A is nothing else but a linear combination of these two vectors that I'm wiggling here. In other words, what we have found is a generating set for this collection. And it's not only that, it's not only a generating set, it's actually a base. Because the collection forms a linearly independent set, and that's something that we can verify simply by the row reduction process. So, the collection 1, negative 3/2, 1, 0, comma, 1, negative 1, 0, 1 is a basis of the null space of A. Okay, so we're done with the first one. Okay, what about the range? Well, for the range, it's a slightly different story. But let's start. Recall, or remember, that the range of A is described in the following terms. This is the collection of all those vectors in R3 such that A times X is equal to Y for some Y, I'm sorry, not for some Y, but for some X in R4. Well, let's work this out a little bit. Let's interpret it in different terms. And we're going to write the elements of this set in this fashion. Y1, Y2, Y3. Why is that I can do that? Because I know the number of components that it possesses. So, we need to determine the consistency of the system defined by this 1, 2, 2, 1, 2, 2, 1, 0, 1, 0, negative 1, negative 1, times x1, x2, x3, x4 equal to y1, y2, y3. Why? Why is this? Because in order for something, for a vector to be in the range of A, it should come as the product of another vector in R4 with this matrix. Right? So, how is that we can proceed? Well, in the following way. Remember that consistency of a system is associated with the number of with their 0 rows to the left of an augmented matrix. So, let me summarize it in this case. So we may resolve the consistency of the system by finding the row reduced echelon form of the augmented matrix A with Y. And check the 0 rows. And here 0 in quotations because there are zeros only on the left of the augmented part. Okay, so let's proceed. How should we continue? Well, look, what I'm going to do here is to save some work. We already know the steps that we have to follow in order to achieve the row reduced echelon form of this matrix. Why is that? Well, for this reason. Those are exactly the ones that we followed here in this reduction process. So what I'm going to do is just to save some work. Include the operations, but only indicate the manipulation on the symbols y1, y2, and y3, just to save some space. So let's proceed. Okay, so instead of writing the full matrix, I'm going to write a few dots, the augmented part, and then as things are needed, I'm going to represent them accordingly. So first, those two operations, we have row 2 minus 2 row 1, and row 3 minus row 1. And that results in a new matrix, but what is important is to keep track of what happens to the column. So we have y1, y2 minus 2 y1, and y3 minus y1. Next, we apply this operation, row 3 minus row 2. So now we have another matrix here, followed by y1, then y2 minus y minus twice y1, y3 minus y1, minus y2 minus 2 y1. Then from here, we apply the following operation, negative 1/2 of row 2. Well, we have a matrix, and then we look at the column, y1, negative 1/2 of y2 plus y1, and then a simplification of the expression that we have here symbolically. So this is just y3 minus y2 plus y1. And an additional step, which is the last one, we have row 1 minus 2, row 2. And from here, well, now I'm going to explicitly indicate the matrix that we obtain. So we have 1, 0, negative 1, negative 1, 0, 1, 3 halves, 1, 0, 0, 0, 0. Why is this? Because those are exactly the steps that we followed before. Except that now we have a different augmented column, which is given by this. y1 minus 2 times negative 1/2 of y2 plus y1, followed by negative 1/2 of y2 plus y1, and then y3 minus y2 plus y1. But you see, it's only this column, it's only this row that tell us something important about the consistency of the original system. So, a times x equals y is consistent if and only if, well, y3 minus y2 plus y1 is equal to 0. I'm going to rewrite this as follows. y1 equals y2 minus y3. Now, in fact, we reduce the problem of finding a basis of R A, the range of A, to that of finding a basis for the null space of this row matrix 1, negative 1, 1. You may say, why? Well, look. This is y1, this is y2, and this is y3. So, in general, we reduce the problem of finding a basis for the row space, for the range of A, to that of finding the null space of another matrix. In this case, the equations are simple enough so that we can explicitly write things out. So, we have y1, y2, y3 belongs to the range of A if and only if y1 minus y2 plus y3 is equal to 0, which happens exactly when y1 is equal to y2 minus y3. And just as before, we can explicitly rewrite the following. This happens if and only if y1, y2, and y3 is equal to y2 minus y3, y2, y3, which we can decompose as y2 times 1, 1, 0, plus y3 times negative 1, 0, 1. So, the set 1, 1, 0, negative 1, 0, 1 is a minimal spanning set of the range of A. Namely, it is a basis. And we can verify that the nullity is equal to 2 And the rank of this matrix is also equal to 2. And when we add them, that results in the number of columns of the original matrix. This is nothing else but a verification of the dimension theorem. Okay, so now, what about the row space? Well, the row space, it's even easier. Why? Because we already did everything. We just have to collect the non-zero rows in the row reduced echelon form of A. In other words, the row space of A is nothing else but the span of the following set. 1, 0, -1, -1, comma, 0, 1, 3/2, 1. Imagine that you simply perform the same operations that we did at the very beginning, but without the augmented 0 vector. Okay? But then, let's not just take it here, because this suggests a method. All this to find a basis of the range of A. Why is this? Because the range of A is nothing else but its column space. And how do we transform rows into columns? By taking the transpose. So, let me start like this. In general, let M be a matrix. To find a basis of the range of A, also known as, in this case, as the column space of A, we proceed in the following way. First, take the transpose. Second, calculate the row reduced echelon form of M transpose. Then, after this, collect the non-zero columns, the non-zero rows, and transpose them. To form a set S. This set is a basis of the range of M. All this in virtue that, well, row equivalent matrices have exactly the same row space. But how do we transform rows into columns? By taking matrices. It's just that we have to recover that information at some point. Okay, now the advantage of this method might be that we are not longer doing symbolic computations. This is simply numerical. And we're avoiding the step that we have to recalculate a basis for the null space of another matrix. So this saves a lot of work. Okay, so let me stop with this at this point, and I hope that you like it. Take care, subscribe, and I'm looking for your comments. See you later.